The world, 66 million years ago, was a planet of giants. In the closing moments of the geological chapter known as the Cretaceous Period, life had achieved a state of magnificent, stable complexity. This was the Maastrichtian Age, the final act in the Mesozoic Era, an era that had belonged unequivocally to the dinosaurs for over 150 million years. The continents, though closer to their modern positions than in the time of the Jurassic, were still arranged differently. A vast inland sea, the Western Interior Seaway, split North America into two landmasses, Laramidia to the west and Appalachia to the east. The climate was warmer and more uniform than our own, with lush polar forests and no permanent ice caps. Atmospheric oxygen levels were higher, contributing to a vibrant and energetic global ecosystem. This was a greenhouse world, a planet teeming with life forms, both familiar and alien. The flora of this era was a mixture of the ancient and the new. Conifers, cycads, and ferns, lineages stretching back into deep time, still dominated many landscapes, forming dense, dark forests. However, a recent evolutionary innovation was rapidly conquering the globe: the angiosperms, or flowering plants. They diversified the world's color palette with blossoms and introduced new food sources with fruits, co-evolving in a complex dance with insects and small vertebrates. This botanical revolution was restructuring ecosystems from the ground up, creating new niches and opportunities. Great forests of magnolias, laurels, and primitive sycamores covered vast swathes of land, forming the base of an intricate food web. Upon this vibrant green stage moved a cast of animals of incredible size and diversity. The non-avian dinosaurs were the undisputed masters of the terrestrial realm. In North America, the famous Hell Creek Formation provides a detailed snapshot of this lost world. Here, the colossal Tyrannosaurus rex, a predator of immense power and sophisticated sensory capabilities, reigned at the apex of the food chain. Its 7-ton frame and bone-crushing jaws were the product of millions of years of evolutionary refinement. It was not a lumbering brute, but an active, dynamic predator, perfectly adapted to hunt the large herbivores of its time. Its prey were equally spectacular. The three-horned Triceratops horridus, a walking fortress of bone and keratin, moved in herds. Its massive frill, not just for defense, but likely for display and species recognition. They were bulk feeders, their powerful beaks and batteries of teeth capable of shearing through the toughest cycads and ferns. Alongside them were the hadrosaurs, the so-called duck-billed dinosaurs like Edmontosaurus. These were colossal herbivores, some reaching lengths of over 15 meters, living in vast herds and communicating with complex vocalizations through hollow crests. Smaller, but no less impressive, were the armored Ankylosaurus, covered in osteoderms and wielding a devastating bony club at the end of its tail, and the fleet-footed ornithomimids, which resembled giant flightless ostriches. The ecosystem was rich with raptors, such as the formidable Dakota raptor, a large dromaeosaur that posed a threat to even medium-sized dinosaurs. This was a world of high-stakes survival, a complex interplay of predator and prey that had been finely balanced for eons. It wasn't just the giants that thrived. The undergrowth teemed with smaller dinosaurs, early mammals no larger than badgers, scurrying lizards, snakes, and amphibians. These mammals were not the cowering, primitive creatures of popular imagination. They were a diverse group, occupying niches as burrowers, climbers, and even swimmers. But their evolutionary potential was held in check by the overwhelming dominance of the dinosaurian megafauna. The skies belonged to the pterosaurs, the flying reptiles. By the late Cretaceous, they had produced the largest flying animal of all time, Quetzalcoatlus northropi. With a wingspan rivaling that of a small airplane, these giants soared over the inland plains, hunting small dinosaurs and other vertebrates on the ground. The seas were no less alien and magnificent. Giant marine reptiles called mosasaurs, some stretching to over 17 meters long, were the apex predators of the oceans, their double-hinged jaws allowing them to swallow enormous prey. Plesiosaurs, with their long necks, patrolled the waters, while the oceans were filled with ammonites, shelled cephalopods related to modern squid, and a vast diversity of fish, including sharks of impressive size. The very base of the oceanic food web consisted of microscopic organisms like foraminifera and coccolithophores, whose calcareous shells, over millennia, formed the chalk deposits that give the Cretaceous period its name. This was a world in its prime, a mature and stable biosphere forged by millions of years of evolution. There were no omens, no warnings of the apocalypse that was approaching. The volcanoes of the Deccan Traps in what is now India were active, spewing gases into the atmosphere and causing some regional environmental stress. But this was a slow geological process to which life was gradually adapting. The dinosaurs, pterosaurs, and mosasaurs were not a failing lineage on the verge of decline. They were successful, diverse, and globally dominant. They had weathered climate shifts, sea level changes, and other challenges for over 150 million years. To any observer on that fateful day, there was no reason to suspect that their reign was about to end in a matter of hours. Unseen and unheard, a visitor from the depths of space was on a terminal course with this vibrant world. It had been traveling for millions, perhaps billions of years, a stray remnant from the formation of the solar system. It was an asteroid, a city-sized mountain of rock and metal, approximately 10 to 15 kilometers in diameter. Traveling at a hypersonic velocity of around 20 kilometers per second, so fast it could cross the Atlantic Ocean in under 5 minutes, it carried an almost unimaginable amount of kinetic energy. It was a cosmic bullet, and Earth was in its path. As it screamed through the final 100,000 kilometers of its journey, the space between the Moon and Earth, it remained invisible to the creatures below. There were no telescopes, no astronomers to chart its deadly trajectory. For the inhabitants of the Cretaceous world, the sky was a familiar canopy of sun, moon, and stars, a predictable cycle of day and night. The first and only sign of the impending catastrophe would be the moment of its arrival. The object approached not from directly above, but at a steep, lethal angle of about 60 degrees. This specific trajectory would prove to be exceptionally destructive, maximizing the amount of vaporized material ejected into the atmosphere. The target was a shallow tropical sea, the body of water that would one day become the Gulf of Mexico, just off the coast of the Yucatan Peninsula. The bedrock here was not inert granite. It was a layered platform of carbonate and evaporate rocks, particularly limestone and gypsum, rich in carbon and sulfur. This geological happenstance would transform a terrible impact into a global extinction event. In the final second of its journey, the asteroid tore through Earth's thin atmospheric shell, compressing the air in front of it into a plasma hotter than the surface of the sun. For a single fleeting moment, a new, brighter star appeared in the day-lit sky over the Americas. Then, it struck. The moment of contact, the instant the asteroid touched the shallow waters off the Yucatan Peninsula, was a planetary-scale event that defies easy comprehension. The energy released was staggering, estimated to be the equivalent of over 100 trillion tons of TNT, or several billion times the power of the atomic bomb that destroyed Hiroshima. In that first fraction of a second, the very laws of physics, as they apply to conventional materials, were obliterated. The asteroid and a vast volume of the Earth's crust did not shatter or crumble. They vaporized. The kinetic energy of the impactor, a function of its immense mass and velocity, was instantaneously converted into heat and a shockwave of unimaginable force. The temperature at ground zero soared to tens of thousands of degrees Celsius, far hotter than the sun's surface. A deep bowl of the planet's crust, nearly 30 kilometers deep and 100 kilometers wide, was instantaneously excavated. The shallow seawater at the impact site was flashed into superheated steam and ceased to exist as a liquid. The asteroid itself, along with a massive portion of the underlying carbonate and sulfate-rich rock, was subjected to pressures millions of times greater than normal atmospheric pressure. They underwent a phase change, transforming directly from solid to a superheated plasma gas. This was not a crater being dug. It was a section of the planet being erased and converted into a plume of incandescent vapor. This entire process of initial penetration and vaporization took less than 2 seconds. The initial crater formed by this excavation is known as the transient crater. It was a profoundly unstable structure, a vast, deep cavity in the Earth's lithosphere. As the shock wave propagated downwards and outwards, it violently pushed aside rock, compressing it beyond its elastic limits. Rock, for an instant, behaved like a liquid, flowing and splashing away from the point of impact. The seismic energy released was equivalent to an earthquake of a magnitude greater than 11 on the Richter scale. No earthquake in recorded human history has even approached this level of power. It was an impact that literally shook the entire planet to its core. The initial flash of light from this event was the most brilliant single light source to have appeared on the planet's surface in billions of years. Any living creature with a direct line of sight within a radius of hundreds of kilometers was instantly and silently incinerated by a wave of thermal radiation traveling at the speed of light. This was not a fire. It was pure, intense energy, a thermal pulse that would have vaporized soft tissue and flash-boiled the fluids within any organism caught in its glare. The Tyrannosaurus hunting on the coastal plain, the Quetzalcoatlus soaring high above, the Triceratops herd grazing in the forests. If they were within this immediate kill zone, their existence ended before the sound of the impact could ever reach them. Their last sensory experience was a light brighter than 1,000 suns. Simultaneously with the thermal pulse, the initial plume of vaporized rock and asteroid began to expand upwards and outwards at hypersonic speeds. This ejecta curtain was not merely smoke and dust. It was a towering wall of plasma, molten rock, and superheated gas, blasting through the atmosphere and into space. The sheer force of this upward explosion was so great that it punched a temporary hole in the Earth's atmosphere, exposing the vacuum of space. A significant fraction of this material was ejected with such velocity that it escaped Earth's gravity entirely, destined to orbit the Sun, some of it eventually landing on other planets and moons of the solar system. Rock from Cretaceous Earth may, to this day, rest on the surface of Mars or the moons of Jupiter, a silent testament to the violence of that moment. But most of the ejecta did not escape. It was lofted high on ballistic trajectories, destined to fall back to Earth across the entire globe. This included everything from fine dust particles to city block-sized chunks of bedrock torn from the planet's crust. Closer to the impact site, the material being thrown out was immense. The shock wave propagated not just through the ground as a seismic event, but also through the air as a cataclysmic blast. This atmospheric shock wave was a moving wall of compressed air, expanding away from ground zero at speeds far exceeding the sound barrier. It was a wave of pure force, capable of leveling forests, scouring the landscape of all life and soil, and generating winds of unprecedented ferocity. Nothing could survive its passage. In the first few minutes, the transient crater began a dramatic and violent process of collapsing in on itself. The superpressurized rock at the base of the cavity, its structural integrity momentarily destroyed, rebounded upwards like a water droplet struck by a stone, but on a geological scale. This central uplift, a mountain range of molten and shocked rock, momentarily rose higher than Mount Everest before collapsing back down and outwards. This rebound and collapse formed a distinctive feature known as a peak ring, a circular ridge of hills inside the main crater rim. The Chicxulub crater is one of the best preserved examples of such a structure in the solar system. The entire formation of the final crater, a structure nearly 200 kilometers in diameter and a kilometer deep, was complete within minutes. An immense circular scar had been carved into the face of the planet. centered on what is today the town of Chicxulub Pueblo. For life within a 1,000-kilometer radius of the impact, the first minute was the last. The combination of the thermal pulse, the air blast, and the ground-shaking seismic event created a zone of absolute annihilation. It was a multi-pronged assault of energy from which there was no shelter and no escape. But the true global reach of the catastrophe was only just beginning to unfold. The material thrown high above the atmosphere, the heralds of a global doom, was starting its inevitable return journey. The immediate regional devastation was horrific, but it was the global consequences unleashed in these initial moments that would ultimately rewrite the course of life on Earth and seal the fate of the dinosaurs. As the newly formed crater shimmered under an apocalyptic glow, a series of cascading planet-altering events began to propagate outwards. The displacement of a colossal volume of water and crust by the impact initiated one of the largest tsunamis in Earth's history, a mega tsunami. Where the asteroid struck, the sea was vaporized, creating a vast cavity. As the crater walls stabilized, ocean water rushed back into this superheated bowl, generating a series of gargantuan waves. The initial wave radiating from the impact's periphery may have reached a truly biblical height, possibly hundreds of meters tall. Some models suggest it could have been over a kilometer high close to the source. It was not a wave of water in the conventional sense, but a turbulent wall of debris, mud, and superheated steam. This wave scoured the floor of the Gulf of Mexico, ripping up sediments that had accumulated over millions of years. It radiated outwards at the speed of a jet airliner. When it made landfall on the coastlines of the Yucatan, Florida, Cuba, and what would become Texas and Mexico, it did not break. It annihilated. The wave penetrated hundreds of kilometers inland, a liquid bulldozer that stripped landscapes down to bare rock, sweeping away entire forest ecosystems, along with every living thing within them. The incredible energy of this wave is recorded in the geological record. Massive tsunami deposits, known as chevrons, can be found far inland throughout the Caribbean and the Gulf Coast region, containing a chaotic mixture of deep ocean microfossils, wood from terrestrial forests, and spherules from the impact itself, a testament to the wave's sheer power and reach. This was just the first wave. The sloshing and reverberation of water within the Gulf Basin and the subsequent earthquakes would have generated a series of powerful tsunamis for hours and days afterwards, continuing to pummel coastlines. The effects were not limited to the Gulf of Mexico. The tsunami propagated into the Proto-Atlantic Ocean, and the immense seismic shock from the impact would have triggered submarine landslides and sympathetic tsunamis in oceans across the globe, reaching even the distant shores of the Pacific. While the seas were in turmoil, an even more sinister event was unfolding in the skies. The vast plume of vaporized rock and asteroid that had been blasted into and above the atmosphere now began to fall back to Earth under the pull of gravity. This material included microscopic dust, sand-sized droplets of molten rock that cooled into glass beads called microtectites and spherules, and larger fragments of rock. As these trillions upon trillions of tiny particles re-entered the atmosphere on ballistic trajectories all around the world, they behaved like a global meteor shower of unprecedented intensity. Traveling at high speeds, the re-entering particles compressed the air in front of them, heating up to incandescent temperatures through friction. This process transformed the upper atmosphere into a gigantic planet-sized radiant heater or broiler. The sky itself began to glow an ominous dark red. The energy released by this re-entry heat pulse was immense, significantly raising the temperature of the air at ground level globally. Estimates suggest surface temperatures could have risen by tens of degrees for several hours. For any animal exposed on the surface, this would have been a lethal event. The air would become too hot to breathe, and the intense infrared radiation would have cooked exposed flesh. Small animals could have sought refuge by burrowing underground or sheltering in deep water, but large terrestrial animals like the dinosaurs had nowhere to hide. The consequence of this global heat pulse was fire. The superheated sky acted like a magnifying glass focusing the sun's rays on every flammable object on the planet's surface. Dry leaves, dead wood, entire forests. They began to smolder and then erupt into flame. What started as localized fires quickly coalesced into continent-spanning firestorms. Evidence for these global wildfires is preserved in the KPG boundary layer itself, which contains a thin, dark stratum rich in soot and charcoal, the fossilized remnants of a burned world. This soot layer is found in geological sites across the globe, from North America to New Zealand, indicating a synchronous worldwide conflagration. The planet's lush green ecosystems were being systematically incinerated. In the first few hours following the impact, the world was subjected to a hellish combination of catastrophes. Coastlines were being battered by colossal waves. The ground was shaking from the single largest earthquake in known history and its countless aftershocks. And the very air was hot enough to ignite the world's forests. And the sky, which moments before had been a familiar blue, was now filled with the returning ejecta and the thick black smoke of burning continents. Daylight began to fade, not with the gentle passing of evening, but with the rapid and suffocating blanket of an artificial night. The key to the global nature of this extinction event lies in the unique geology of the impact site. The asteroid did not strike geologically inert granitic crust. It struck a thick platform of sedimentary rock rich in sulfur-bearing minerals like gypsum, calcium sulfate, and anhydrite. The immense heat and pressure of the impact vaporized these rocks, releasing a colossal quantity of sulfur aerosols, specifically sulfur dioxide and trioxide, directly into the stratosphere. Estimates suggest that anywhere from 100 to 500 gigatons of sulfur were instantly injected high into the atmosphere. For comparison, the 1991 eruption of Mount Pinatubo, one of the most significant volcanic eruptions of the 20th century, which caused a noticeable temporary global cooling, released only about 20 megatons of sulfur dioxide. The Chicxulub impact released at least 10,000 times more. In the stratosphere, these sulfur gases reacted with water vapor to form tiny droplets, or aerosols, of sulfuric acid. Unlike the heavier ejecta, which fell back to Earth within hours, these aerosols were incredibly fine and could remain suspended in the stratosphere for years, even decades. They formed a persistent global haze that efficiently blocked and scattered incoming sunlight. This was the beginning of the impact winter. The soot from the global wildfires, also lofted high into the atmosphere, compounded this effect. A dark, toxic shroud was drawing itself around the entire planet. The immediate fiery phase of the extinction was giving way to a new, long-term phase of cold and darkness. Within hours of the impact, the sun began to disappear from view, and the Earth was plunged into a profound, chilling twilight that would last for years. Photosynthesis, the fundamental process that powered nearly every ecosystem on the planet, was about to shut down on a global scale. The food chain was about to be severed at its very base. The first hours of the Cenozoic Era, the age of mammals, had begun, but it started with darkness, fire, and the deafening silence of a dying world. The immediate violent phenomena of the first few hours, the blast, the tsunamis, the rain of fire, were the initial blows that caused widespread, instantaneous death. But it was the profound and lasting changes to the global climate and atmospheric chemistry that systematically dismantled the Cretaceous world and ensured the extinction of an estimated 75% of all species on Earth. The primary kill mechanism for the long term was the impact winter, a direct consequence of the material injected into the stratosphere. The veil of sulfuric acid aerosols and fine soot from the wildfires spread rapidly from the impact hemisphere across the entire globe, carried by stratospheric winds. Within days to weeks, the planet was enshrouded in a dense blanket of particulates that effectively blocked sunlight from reaching the surface. The reduction in solar energy was dramatic. Light levels at the surface may have fallen to that of a dimly moonlit night, and this condition persisted for several years. The consequence of this global darkness was the immediate and catastrophic collapse of photosynthesis. On land, the vast forests of conifers and flowering plants, which formed the base of the food web, could no longer convert sunlight into energy. Plants began to wither and die en masse. In the oceans, the effect was even more swift and devastating. The phytoplankton, microscopic single-celled algae that floated in the sunlit upper layers of the ocean, formed the foundation of the entire marine ecosystem. Without light, they perished on a global scale. The geological record shows a planktonic blackout at the KPG boundary, where fossilized remains of these organisms, abundant for millions of years, suddenly disappear. This cessation of photosynthesis triggered a cascading collapse up the food chain. With the plants gone, the great herbivorous dinosaurs, the Triceratops, the Edmontosaurus, the Ankylosaurus, were left with no food. Their immense size, once an advantage, now became a liability, as they required enormous quantities of vegetation daily to survive. They would have starved to death over a period of months. The starvation of the herbivores, in turn, sealed the fate of the apex predators. Tyrannosaurus rex, for all its power, was doomed once its prey disappeared. The last of these magnificent creatures likely died out in a barren, dark, and freezing world, a shadow of the lush paradise they had once ruled. The impact winter also caused a precipitous drop in global temperatures. With sunlight unable to warm the surface, the Earth's average temperature plummeted. Surface temperatures on land could have dropped by as much as 25 degrees Celsius, 45 degrees Fahrenheit, pushing even tropical regions into freezing or near-freezing conditions for an extended period. The oceans, due to their high thermal mass, cooled more slowly, but the surface waters still experienced a significant temperature drop. This sudden, severe global cooling added another layer of environmental stress that few organisms were adapted to survive. Adding to the darkness and the cold was the problem of acid rain. The colossal cloud of sulfur aerosols in the stratosphere did not remain there forever. It eventually combined with water vapor and precipitated out as highly corrosive sulfuric acid rain. This acid rain would have fallen for years after the impact, devastating any surviving vegetation on land. It would have acidified the surface layers of the oceans, having a catastrophic effect on marine organisms with calcium carbonate shells. This includes the planktonic foraminifera and coccolithophores at the base of the food chain, as well as larger, more familiar organisms like ammonites, belemnites, and reef-building corals and rudist bivalves. Their shells would have literally dissolved in the acidic water. The extinction of the ammonites, a group that had survived for hundreds of millions of years and multiple previous mass extinctions, is one of the most telling markers of the KPG event's unique chemical severity. The impact's location in the carbonate-rich rocks of the Yucatan also released vast quantities of carbon dioxide into the atmosphere. While the initial effect of the aerosols was a deep, chilling winter, once these particles rained out of the atmosphere over the span of a decade or two, the remaining CO2 would have created a powerful long-term greenhouse effect. After the deep freeze of the impact winter, the planet would have swung to a period of intense global warming, with average temperatures significantly higher than pre-impact levels. This wild climatic whiplash from extreme cold to extreme heat presented yet another insurmountable challenge for any ecosystems attempting to recover. Life that might have adapted to the cold would then have been cooked by the heat. In this grim, post-impact world, survival was largely a matter of luck, size, and lifestyle. The survivors were generally small. A small body size meant requiring less food, being able to hide from the worst of the short-term effects, and having a faster reproductive cycle. The mammals that survived were almost universally small, generalist creatures, many of them burrowers or semi-aquatic. Their ability to take shelter underground would have protected them from the initial heat pulse, and provided a more stable thermal environment during the impact winter. A diet not directly dependent on fresh vegetation was key. Many surviving mammals and birds were likely omnivores or insectivores, able to subsist on the vast stores of decaying organic matter, fungi, roots, and insects that could feed on that detritus. In the oceans, organisms living on the seafloor, far from the devastated surface waters and feeding on detritus raining from above, a detritus-based food web, had a better chance of survival than those in the sun-dependent surface ecosystem. The extinction was remarkably selective. On land, no terrestrial vertebrate weighing more than about 25 kilograms, 55 pounds, is known to have survived. All non-avian dinosaurs, from the mightiest sauropods to the smallest raptors, vanished completely. The pterosaurs, the flying reptiles, were also wiped out. In the seas, the giant mosasaurs and plesiosaurs disappeared, along with the ubiquitous ammonites. However, many other groups survived, albeit with heavy losses. Turtles, crocodiles, lizards, snakes, and amphibians proved remarkably resilient. Their lower metabolic rates and, in many cases, semi-aquatic lifestyles likely aided their survival. Most importantly, one group of dinosaurs did survive: the birds. The avian dinosaurs, having already evolved smaller body sizes, beaks, and the advantage of flight, managed to find niches in the ruined world. Likely thanks to seed-eating or other generalist diets. They are the living lineage of the dinosaurs, a direct link to the Cretaceous world. The days, months, and years that followed the Chicxulub impact were a period of unprecedented biological crisis. It was a world of darkness, cold, acid rain, and starvation, punctuated by violent climate swings. The complex and majestic ecosystems of the late Cretaceous, the product of 150 million years of evolution, were fundamentally and irrevocably broken. The impact winter and its associated chemical poisoning were the long, grinding mechanisms of extinction that finished what the initial fire and fury had started. Life on Earth was reset. The fall of the dinosaurs left a vast ecological void, an empty world of opportunity for the small, hardy survivors who had weathered the storm. The story of the Chicxulub impact is a dramatic tale of cosmic chance and geological vulnerability. Yet, for much of human history, the cause of the dinosaurs' demise was one of science's greatest unsolved mysteries. For over a century after the first dinosaur fossils were identified, paleontologists debated theories ranging from gradual climate change and disease to volcanic activity and even the evolution of egg-eating mammals. The clues to the true cause were there, written into the rock strata of the planet. But they were subtle and awaited the right scientific tools and insights to be read correctly. The breakthrough came in the late 1970s. A team led by the father and son duo, Luis and Walter Alvarez, a physicist and a geologist respectively, were studying a thin layer of clay at the boundary between the Cretaceous, K, and Tertiary, T, now more commonly called the Paleogene, PG, periods in Gubbio, Italy. This KPG boundary layer marked the precise geological moment of the Great Extinction. They were attempting to determine the rate of sediment deposition and decided to analyze the concentration of the element iridium in the clay. Iridium is a metal that is rare in Earth's crust, but is far more abundant in extraterrestrial objects like asteroids and comets. They expected to find a vanishingly small, constant background level of iridium. Instead, their results were astonishing. The thin boundary clay contained a concentration of iridium that was hundreds of times greater than the surrounding rock layers. This iridium anomaly was so striking that it demanded an extraordinary explanation. The Alvarez team calculated that a slow, terrestrial process could not account for such a sudden spike. They hypothesized that the iridium was the fallout from the impact of a massive 10-kilometer-wide asteroid that had vaporized on contact with Earth. They proposed that the resulting dust cloud had enveloped the planet, blocking sunlight and causing the mass extinction. This extraterrestrial impact hypothesis, published in 1980, was revolutionary and initially met with considerable skepticism from the scientific community. Many geologists favored the volcanic theory, pointing to the immense and contemporaneous eruptions of the Deccan Traps in India as a more plausible Earth-based cause. The search was on for confirming evidence, particularly the smoking gun, a massive impact crater of the correct age. The search for the crater took another decade. Geologists had noticed gravitational and magnetic anomalies in a semicircular pattern on the northern coast of the Yucatan Peninsula in Mexico as early as the 1950s during surveys for petroleum. It wasn't until the late 1970s that geophysicists Glenn Penfield and Antonio Camargo, working for the Mexican state oil company Pemex, identified the feature as a possible impact crater. Their findings, however, were not widely known outside the petroleum industry. It was only in the early 1990s that journalist Carlos Byers connected the work of Penfield with the Alvarez hypothesis. Alan Hildebrand, a Canadian geologist, followed these leads and, by studying unique KPG boundary deposits in the Caribbean that clearly pointed to a nearby source, pinpointed the buried Yucatan structure as the long-sought crater. He named it Chicxulub, after a nearby town. Subsequent research, including extensive drilling into the buried crater by international scientific teams, has provided overwhelming confirmation. Core samples from the crater reveal a sequence of events that perfectly matches the impact scenario. They show the shocked and melted bedrock of the Yucatan overlain by fallback breccia, the jumbled rock that fell back into the crater immediately after the impact. Above this are sediments deposited by the returning megatsunami, and at the very top is the iridium-rich clay layer that marks the final settling of dust from the global cloud. The age of the melted rock in the crater has been dated radiometrically to precisely 66 million years ago, a perfect match with the KPG boundary found all over the world. Today, the Chicxulub crater is almost entirely invisible from the surface. It is buried beneath a kilometer of younger Cenozoic sedimentary rock. However, its presence can still be traced. The overlying limestone has settled and fractured along the lines of the buried crater rim, creating a subtle surface depression. This has influenced the flow of groundwater, resulting in a nearly perfect arc of cenotes, natural freshwater sinkholes, that perfectly delineates half of the hidden crater's rim on the Yucatan Peninsula. These beautiful water-filled caverns, popular with tourists and locals, are the only visible surface expression of the geological scar left by the single most destructive event in the last 100 million years. The discovery of the iridium anomaly and the Chicxulub crater represents a profound shift in our understanding of Earth's history. It confirmed that the evolution of life is not a slow, stately progression, but a history punctuated by rare, catastrophic events that can fundamentally reset the biosphere in an instant. The impact was not just a historical event. It is a timeless lesson in cosmic vulnerability and the delicate contingency of our own existence. The extinction of the non-avian dinosaurs, pterosaurs, and mosasaurs was a profound tragedy for those magnificent lineages, ending 150 million years of evolutionary success. But it was also the single most important event in the history of our own lineage. The KPG extinction was the great liberator of the mammals. For tens of millions of years, they had existed in the shadows of the dinosaurs, their size and diversity constrained by the dominant reptilian megafauna. With the giants gone, a planet of vacant ecological niches opened up. In the millions of years that followed the impact winter, the surviving mammals, small and adaptable, exploded in a spectacular burst of evolutionary diversification known as an adaptive radiation. They evolved into new forms to fill the empty roles. There were now new opportunities for large herbivores, for fleet-footed predators, for swimmers, and for flyers. Out of this post-apocalyptic crucible arose the ancestors of all modern mammal groups, from whales and bats to horses and cats. Among the survivors was a small, unassuming group of mammals that had taken to the trees, the primates. Over the next 66 million years, this lineage would continue to evolve, eventually producing a species with the capacity to understand the very cosmic forces that had cleared the way for its own ascendance. The story that began with a stray asteroid and ended with a global winter is, therefore, our own origin story. Every human being alive today, every city we have built, every thought we have ever had, is a consequence of that one terrible day. The first few minutes after the impact, when a portion of the planet was vaporized and the sky caught fire, did more than just mark the end of the age of reptiles. They marked the improbable and violent beginning of the age of mammals, and ultimately, the age of man. The Earth still bears the scar, a quiet reminder that the history of life is written not only by the slow processes of evolution, but also by the sudden, terrifying violence of the cosmos. The dinosaurs' extinction serves as a stark testament to the fact that on geological timescales, even the mightiest rulers of the world can be dethroned in a single, catastrophic moment, leaving the stage clear for the next act in the long and unpredictable drama of life.